One of our definitions of the Brouwer order involves multiplying a permutation by transpositions and having the length go up by 1 each time we multiply by a transposition. Now I want to look at the possibility that those transpositions are all adjacent transpositions, that is, generators of the symmetric group. So recall that U is less than or equal to W in the Brouwer order. If the length of W is equal to the length of U plus P, and there exist transpositions T1 through TP such that W equals TP through T1 U. That is, we multiply U by T1 first, and then T2, and then T3 up to TP. And at every step, when we multiply by one more transposition, the length goes up by 1. So the length of Ti through T1 U equals the length of Ti minus 1 through T1 U plus 1 for all I. So the question is, for multiplying by a transposition and going up by 1 each time, can these transpositions all be chosen to be adjacent transpositions? So can all the transpositions be chosen to be adjacent transpositions? Say J plus 1, which is the generator little sj of the symmetric group. The answer is not always. Let's look at one example. Well, to justify not always answer, all you need is one example. So 1, 4, 5, 2, 3 is greater than 1, 2, 5, 4, 3. Because 1, 4, 5, 2, 3 can be written as 1, 2, 5, 4, 3, and then we left multiply by, I'm swapping the positions in, swapping the letters in positions 2 and 4. Which also happen to be the letters 2 and 4. So it takes one transposition to get from 1, 2, 5, 4, 3 to 1, 4, 5, 2, 3, whether you multiply on the left or the right. I didn't mean to make this example have those numbers come out exactly the same, but that's the way I wrote it. And let's see, the length of 1, 4, 5, 2, 3 is 4 is greater than 2 things to its right, so is 5. So that's length 4. And the length of 1, 2, 5, 4, 3 is 5 is greater than 2 things to its right, 4 is greater than 1 thing to its right, 3. So the length did go up by 1. And there is not a way to get from this shorter permutation to the longer one by multiplying on the left or on the right by just a generator. But if the lower permutation is the identity, then we can just use adjacent transpositions. And the reason is we can choose a reduced expression for W let me write it as SIP through SI1. U is the identity. Then we have W equals this times the identity. And SI J through SI1 has length equal to Sij minus 1 through Si1 plus 1. So obviously every time we add a generator we're making the length go up exactly 1. And we actually can define a slightly different post set on the symmetric group called the weak order using these adjacent transpositions. So W is greater than or equal to U if the length of W equals length of U plus P, and there is a sequence SIP through SI1 of generators. Satisfying W equals SIP through SI1U. I guess we could call this the left weak order because we're multiplying on the left, and there's a right weak order also. So let's call this the left weak order. The right weak order is defined by W being equal to U times SI1 through SIP on the right. And this is isomorphic to the left weak order. But not equal to it. So, for example, on S3, we have S1, S2, S1 equals S2, S1, S2 on top, and the identity element on the bottom. And then if we use the left weak order, multiply E on the left by S1 or S2, multiply that on the left by S2 or S1, and then multiplying this on the left by S1, that on the left by S2, and then we go up to this top element here. We do not have an edge from S1 to S1, S2 because we can't multiply that on the left by something to get S1, S2. But if we multiply on the right instead, we multiply S1 on the right by S2, we get S1, S2. Just writing it on the right because that's where it is over here. If we multiply S2 on the right by S1, we get S2, S1. Now S1 is not less than S2, S1 because we can't multiply S1 by something on the right to get S2, S1. Now if we open up that post set and twist it around, we'll see it looks just like the other one. But it's not the case that the elements are related to each other exactly the same way as they are in this post set. The end.